Our next video, as we look through the gases and gas laws, is going to deal with Graham's law. This is something, again, you covered in pre-AP. Not always the student's most favorite gas law, but I think it's because you get hung up on the math. We're going to go over the math, hopefully simplify it for you. But after this, I hope you feel really comfortable with Graham's law. There's not always a lot of questions on the AP test about Graham's law. In fact, there could be 1 or 2 years between questions. But it's still good to understand what's going on. When we're talking about Graham's law, we're really talking about the movement of the particles in a gas. The actual motion, like a speeding car down the highway, that kind of movement. And if you remember from the kinetic molecular theory, that gases are in constant random motion, and they continue in a straight line until they bounce off of something else and change direction. There are a few collisions between particles. That's part of kinetic molecular theory also. Particles do collide, but part of the KMT says that those collisions are infrequent. It's more common for the particles to collide with the walls of their container. So the two words that Graham's law sort of applies to, Graham's law is really made for effusion. We use Graham's law for diffusion, but technically it doesn't work out perfectly. It's only an approximation for diffusion, but it works splendidly for effusion. Let's talk about those two terms. As you see from the what's on the screen here, effusion is the escape of gas particles through a tiny opening. Look at the picture at the top of the page. You've got two cylinders here with gases in it, and the one on the left, this one, there's a tiny opening here. And on the right, there's a much larger opening. You would see effusion through the left one and not the right one because of the size of the opening. If the opening's too big, you get like diffusion taking place, like bulk, like lots of the particles will start traveling through the hole because the hole is so many times larger than the mean free path, and it goes into some more complicated physics. But just know, if it's a big hole, like a lot of the gas, the whole cloud will start moving through, whereas if it's a tiny hole, there is a specific rate of how many of those particles can hit the hole in a certain amount of time. So we have effusion, the escape of gas particles through a tiny opening. It is related to a pressure gradient. So the more particles you have up here in this area, you'll have more chances for a particle to hit the hole. And the number of, we learned with Dalton's law that the number of moles is proportional to pressure. So it's sort of a, it's related to pressure gradient. Diffusion is something you learned about in biology. It's a bulk movement, in this case of a gas, from high to low concentration. In biology, you probably learned more like ions, like the sodium-potassium pump follows a concentration gradient. That's diffusion. Osmosis is a type of diffusion. But the main idea is that it moves from a high concentration to low along the concentration gradient, but it's a bulk movement. There's a lot of particles instead of like one at a time. The main idea, though, no matter what, is this. Heavier gases move slower than lighter gases. That's what I want you to take away from this. Like, you know, just like human beings, sumo wrestlers, big, heavy people, don't run as fast as light, thin people usually, almost all the time. So heavier gases move slower. There's an inverse proportion between mass, molar mass in this case, and the speed of the particles. And it's inverse square root. So we can say it like this, rate, and we have the inverse proportion. So it looks kind of like a Boyle's law. But then we add the additional, it's not fully inverse, it's inverse squared. That's the Graham's law proportion. Alright, I'm going to play a couple of videos here. Try not to be too tedious, just going to show a couple of applications of Graham's law. Just watch real quick. So as you see from this video, that the helium, because it's so much lighter than the average size of a gas, so for air, the average molecular weight is 28 grams per mole. That's a lot heavier. So the helium will effuse. The particles will move that much faster coming out of the little tiny holes at the top, in this case, and you can see it shrunk a lot faster. And you can see it's about 2.5 times smaller at this point than the other one. Now this hole here is a little large, so it goes a little bit beyond that pinhole leak, but you still see the idea of the rate of effusion. Now we're going to watch a little demo here of two gases that are going to react. So this guy is going to put ammonia on one end of this tube and HCl on the other end, and of course the gases are going to move. They're going to move toward each other, and we're going to see that they may not hit right in the middle like you would think. So watch this video.
So I'm going to start with ammonia and hydrochloric acid, and I'm going to start with the heavier gas. Hydrochloric acid is 36 grams per mole. So real quickly, I'm going to add some hydrochloric acid to my cotton. All right. And here's this tube, so I'm going to dip some hydrochloric acid here. And I've got concentrated here today, as opposed to yesterday. Push that into the tube. Okay, I'm going to stop for that now. Alright, next up, I have my ammonia. I've got concentrated ammonium hydroxide today, as opposed to yesterday. Now I'm going to do the same thing. Put some of that up on a cotton ball. And I'm going to push that in. And I'm going to stop with that as well. Now, where these gases meet should give me an idea about the relative rates of diffusion. Ammonia being approximately 17 grams per mole, and hydrochloric acid being approximately 36 grams per mole, should tell me the ammonia is lighter. Therefore, its velocity at the same temperature is going to be greater, and we should be meeting somewhere, I believe, toward the hydrochloric end. Okay? We're going to have to wait a few minutes so we can see that this elapsed time. We look and see that there was clearly an interface between the two gases. And that interface, okay, where these two gases are meeting, is creating that white, cloudy smoke, which is the ammonium chloride. You can see that smoke proliferating. Right, focus a little bit. You'll see that that is clearly on the hydrochloric acid side. And clearly the ammonia is lighter than the hydrochloric acid, and we would expect it to diffuse closer to...
Okay, from that video, you could see the application of Graham's law with diffusion. I told you that Graham's law is not really for diffusion, but you can approximate it, and it might not be exact, but you can see the interface of those two gases was closer to the hydrochloric acid because it's bigger and moves slower. And that's all fine for Graham's law use there. Let's look now at the math relationship. The math relationship, we talked about this as an inverse square root law with rate. So we can see here that we can use this formula, rate times the square root of the molar mass. This looks kind of like a Boyle's law relationship that was also inverse, where you have the two variables right next to each other. So rate 1 times molar mass 1 equals rate 2 times molar mass 2. So that way, writing it like this might be beneficial to you because it looks like a Boyle's law problem with P1 V1 equals P2 V2, and that's also inverse. So that just help you remember that. Another way that you might prefer to use the Graham's law setup is to write it like this. I'm not a huge fan of this. This is, over the years, has caused students some trouble because they have to remember, if you set it up like this, since they're inversely proportional, the square root of m1 will be on the bottom on the other side, the far side of the equal sign. So I just kind of drew a diagonal here. You have to remember they're diagonal from each other if you set it like that. Either way that you want to work it, it's up to you. Now we can also use Graham's law to find time, not just rate. Rate is a distance traveled over time. So sometimes you just want to know, like, how long does it take? Just a straight up time. Now, rate is inversely proportional to the mass, but time is actually directly proportional to the molar mass. So you have a completely different setup here. This is going to be more like your Charles law or Gay-Lussac's law, where the direct proportion. So you see I have time 1 on top of square root of m1. And so you can set up like this, where it looks like a Charles or Gay-Lussac, or you can set it up like this one, where you have to remember again now instead of the diagonal, they're right across from each other. Time 1 on top, square root of m on top. Again, you pick whichever one makes the most sense to you. I actually believe that the way we teach it here, and you guys have learned Boyle's and Charles and how to address inverse versus direct proportions, I think this one makes more sense. That's just my suggestion. For our first example here, just a basic example, we're going to compare neon to butane. So neon gas effuses at 400 meters per second at a given temperature. We want to calculate the rate of effusion of butane, C4H10, at the same temperature. Well, the most important physical characteristic of this is the molar mass. So from the periodic table, I've grabbed neon, 20.18 grams per mole, and then I had to add up butane, C4, and then H10, and that's 58 grams per mole. We can predict that butane is going to have a larger rate of effusion than neon because it's heavier. So we should expect a number smaller than 400 because it's so heavy it's going to be slower. So we plug into our equation. I picked the this form of the equation. So I just copied this over from the previous slide, and I'm plugging in my numbers. 400 for the rate of neon times the square root of its molar mass. This is our variable, and then the square root of the molar mass of butane. And then I just simplify. So I simplified each side, got almost 1800. Square root of 58 is 7.62, and then eventually solve, and I got 236 meters per second for the rate of effusion of butane, and that is much smaller than the initial 400 of neon because it's heavier. All right, you try one of those now. Carbon dioxide travels at 45 meters per second at a certain temperature. The same temperature, find the velocity of an oxygen molecule. Hit pause and try that one. Alright, so as you can see, the most important thing was the molar mass of each, 44 for carbon dioxide, 32 for oxygen. Plug it into the equation in a very similar way here, and you should have gotten 52.7 meters per second for oxygen. You would expect it to be higher because it is lighter. Now this is the type of example problem with Graham's law that kids are more uncomfortable with. As you can see from the title here, sometimes you don't need to know the exact rates. So you're more comfortable probably with solving equations when you have something to plug in for every variable except the one you're trying to solve for. But sometimes in science you're not interested in particular values, you just want to know relative values, like something's twice as big as this one or it's 10 times bigger. And that's the way this problem sets up. An unknown gas diffuses at 0.25 times as fast as helium. So that's not its speed, that's just comparing how it travels to helium. What is the molecular mass of the unknown gas? So for this one we only have helium, so we grab its molar mass, 4 grams per mole, and then we set up. Now to solve this type of problem, go ahead and I use the Graham's law with rates over each other because this is the proportion that I'm being asked to use here in this problem. So this was better than the rate times molar mass way. But either way you work it, it comes out to be the same. So let's plug into this. I'm told that the rate of this unknown gas is 0.25. And just let me point out that I had to write it like this, with X over helium, because the way this problem is read is an unknown gas diffuses at 0.25 as fast as helium. And that's telling me that it's 0.25 over helium. Okay, now if this was twice as fast, it would be 2 over 1. So it would be 2 equals here. So whatever they give you, they're telling you the comparison X to helium. X is on top, helium's on bottom. Alright, so that 0.25 equals the square root of 4 for helium, and then the square root of my unknown. So we're just going to rearrange those variables here. 0.25 times molar mass of unknown equals 2. The unknown square root, the square root of the unknown equals 8. So we get a 64 grams per mole for this gas. It could be SO2 or something like that. It wasn't part of the question, I just threw that in there. So again, the difference of this problem is that when you're looking for proportions, it's easier to use this form, and instead of knowing the actual rates, you can just use these decimal forms or fraction forms. Alright, let's do an example where we look at time, not rates. If helium takes 20 seconds, so there right away we're not dealing with a meters per second, we're dealing with just the time. To effuse through a certain opening, how long will ammonia take? Alright, I want you to work through this one step by step before I do, and see if you can go along with this. First of all, pick out which equations you want to use and go ahead and find your molar masses. Hit pause while you do that. Alright, so those molar masses, helium is 4, ammonia is 17. Did you select which equation you want to use? I picked this one. No real reason, I just grabbed that one. Let's plug in. For helium, we're told it takes 20 seconds, so my unknown is on bottom. And then since we're dealing with time here, helium's on top, its mass needs to be on top. This is a direct proportion. And so I got square root of 4 over square root of 17. So now I just need to do the algebra. But let me make a point here. As I go forward, I'm also going to solve it like I have typed here. But when you have it like this, the algebra is more complicated when your variable's in the denominator. It is perfectly okay to flip this entire thing upside down and have time of ammonia over 20 equals square root of 17 over square root of 4. And that way your variable's already on top. That is a choice you can make. Going through this, I've just rearranged my variables. Hope I did it right. And then simplified, and I get 41.2 seconds. So that's a longer time. Does it make sense? Yes, it's longer than 20 seconds, and I would predict that because ammonia is heavier than helium. So that's Graham's law. It's not too complicated. I just need to get used to setting up and solving that equation. I got some practice problems for you. If you have any questions, let me know.